All right, so let's see, 7, 3. So everybody's got your books. Look at 7, 3. Number 45. Ooh, yeah.
Yeah.
Ooh, yeah.
It's disgusting.
Poor little thing. Didn't ask to be existing. Please solve me. Existence is pain. All right. That one down there, the one about trig sub?
Yeah.
That's bodacious. It almost sucks, the problems where they tell you what the answer is supposed to be. Because you guys give up. You're like, it doesn't look like that. And you're like, no, of course it's not. It's not going to look like that until you get to the end. So it feels as if a problem where they tell you what the answer is should be easier, but a lot of times you guys sort of give up in the middle because you're like, it doesn't look anything like that. Again, it doesn't have to look anything like that, I'll tell you that. So can somebody tell me, let me zoom in on this a little better. Come here, you. All right, focus. Okay, looking at this, notice it is definite. What trig sub would I use? Well, what's my variable first off? T. So what's A? We're assuming it's a constant. I love it. Okay, cool. And that's the importance of this guy. That's why this guy doesn't make any sense without this guy. Especially if you're going to take Calc 3. Because that's where you're going to have a lot of variables, and you have to know at the moment, what am I considering my variable? Okay, so for right now, which is good to know. So what trig sub are we going to use? It sort of gives it away over there. Sine, because I got some number minus function squared, like 1 minus sine squared. Right? Now it's not going to be sine, it's going to be what sine? No. Don't look at that too much.
Sine.
A sine, yes? So that when you square it, the a squared matches up. That is the level you need to be able to reason out the processes we do. So I have no idea how you guys have it memorized. I mean, real quick question. This is a funky question. If I put down here, I'm really zoomed in. That, right? And that's inside of an interval. Okay, maybe zoom out a little bit. Here, just go up. What thought process do you use to figure out what trig sub to use? Now, do you guys agree with me that's a trig sub problem?
Mm-hmm.
Why is it not a U sub problem?
Because you don't have something that has a derivative.
Yeah, what would need to be on the top? Some kind of x. 11x, 48x, negative square root of 11x. 2x would be great, because then that would be perfect, yes? But we don't care about constants. We can make them do whatever we want them to. We made them. I don't have that up there, so U sub's not going to work. So the immediate next thing I can know, this might be related to some kind of arc or something. But the next best thing I have is trig sub. So I think somebody already said it. Since there's a plus, you can bet on it being tangent, because that's the one basic trig identity that has a plus in it. 1 plus tangent squared. Right? So what am I going to make it? I'm not going to make it tangent.
4 tangent?
Why 4 tangent?
Square root of the constant that's there.
Even more generally, it's because when I square this, the constant on it matches the constant that's there. So then I can factor it out. If you take that step back to really see, when they start throwing numbers in front of both of these, you have to know that more general idea. So let me do it right now. Is everybody cool with this? Is everybody cool with this? So you got like 2 levels. You got the what's the basic trig function that's going to work? It's based on the identity. And then what number do I put on there? Right now it's based on this. But more generally, once I square this, the resultant coefficient will match with the number that's there, so I'm able to factor it out. So what do you guys think about this one? dx. You suck, Jeff. What the shit's wrong with you, Jeff? Alright. Do you guys see how you can't just say 5? Real quick. Don't worry about the number. What's the trig function? Sine, because it's like constant minus function squared, yes? Okay, so we know it's going to be something sine. Why is it not just 5 sine?
Because you got something in front of you.
Okay, so do the thing, because I'll put 5 sine, that's 25 times 9 is not 25. You guys see that? So you need to go to that extra, like, next step down, the more fundamental idea. The more fundamental idea is whatever I choose, one's got to be the right trig function to eventually work, and 2, its coefficient has to eventually match with the other number that's in there. So, what number do I wish wasn't there?
The 9.
Damn it, the 9. So, I think we all agree it's a sign. So real quick, don't I want a 5? I know I want some kind of a 5, yes, and what number do I want to die? 9. So why did I want a 5 here? Because when I square it, it's going to become, which is like this one. So what number do I want to die?
9.
So what number do I square to make it 9, but I'm going to put it on the bottom? Yeah, okay, so that's the idea. So when I square that, the 9's going to cancel, and I'm going to end up with the same number that was there. So there's kind of a more basic idea as to what number coefficient to use. Does that make sense? The less you base your ideas on just forms of shit, and the more you base it on what's the idea? Why is there even a form? Why is there something I can memorize? What's the idea? Then you're going to make less mistakes. You're going to memorize less. You're just going to know to do things, the right things. Okay. All right, sorry, I can go on a tangent. I should wear my shirt. I go on a tangent. Yeah. Okay. Did I actually answer the question I was asking?
No.
Oh shit. Okay. I had a feeling I didn't. Oh, well, this is just brute force. Now, you've got your trig sub. Yes. The only thing you got to be careful about, there's t's in there, right? So instead of saying x equals, I'm going to say t equals. So what's t equal?
A sine theta.
Kick ass. And just do that. Just plug it in. Just plug that in. Yes? It works exactly in the same way as other stuff, and to be honest, this has got a lot less going on than some of the other stuff. It's just when you go to plug in, now right now you can change your limits, yes? How would I change my limits? Because what do these limits work for?
T.
T. And of course I'm about to make my variable
Theta.
theta. So how do I figure out what to put here? What should go here? What does this say when what is 0?
When t.
T is 0. So when t is 0, what does sine have to be? 0. How do you make sine? How do you make the output 0? You make the input 0. So that's nice. So my new integral is going to go from 0. Now what if t is x? Here's the part that's going to be really exciting for you.
A sine of x.
No. If t is x, then this must be true, yes?
Yes.
Stop for a minute. And what am I trying to figure out here? This is what t is doing. What do I need here?
What x is doing?
No.
What theta is doing?
I'm going to theta now, right? So can I solve this for theta? Okay.
Yeah.
And you'll see something that looks.
I don't want
How do I solve this for theta?
divide by a and take the inverse sign.
I like the way you say that. Okay. On one level, it should be boring. Yes. I'm not saying you're saying that. You're saying that sort of like in a resigned way, but I love the shit out of it when it's boring. How do I solve for that? Well, I divide by a, and then I undo the sign. So that's the inverse sign. So what do I do with this? Well, I'll tell you what to do with that, Jeff. Hey. What do I do with that? What did I do that for?
Put it.
I don't know.
It's a limit.
It's the limit, exactly. When t was x, theta would be this. I put this there. Yes? Okay. And just keep going. So this is kind of like a brute force little dude. Just gotta do it. And again, it's not gonna look like what it's supposed to until you're almost done, or sometimes until you're done. So don't think you're on the wrong path. Just keep simplifying stuff. Now, you might be on the wrong path, I don't know, but don't give up immediately. Just keep simplifying. Did you get further than that, Sarah, or?
I did some of it in the math.
So you should end up with
sensor,
A cosine theta inside there, yeah? Because when you put A sine theta inside, you factor out an A, you got 1 minus sine squared, which is cosine squared, square root of that is cosine. So you should end up with A cosine theta in that interval with that limit we just figured out there. The integral of cosine is easy. Okay. Maybe. So, real quick, while you guys are all staring at me, let me catch up with. Anybody not get their quiz back yet?
Yay.
So, just to remind everybody, is that everybody? Oh, sorry, not there. Larissa? Thank you. Anytime. So, Cash is not here? No. Okay. Just reminding you guys, you can make corrections, of course. Corrections are due the day of the next test. When is the next test?
Next Thursday.
Yeah, so that's little coming events. So those of you who never had me before, I'll apologize again for my handwriting. I give a practice test out. So this Thursday I'll give a practice test out. Next Tuesday is going to be a review for the test. We won't do anything new next Tuesday. And then Thursday will be the test. So the practice test, you don't have to do it. Don't turn it in. I'm going to give you the answer key. I don't need more paper. You don't have to do it. You can do it if you want to. Try it out. Anyway, okay. We'll talk more about that when we get to the practice test. Anything else? Homework, quizzes?
Can we do 48?
Yes.
I have a feeling that that 48 was meant to be like a challenge, like a extra credit or something.
Oh,
But
it looks like it on first glance, right?
yeah.
A charged rod of length L produces an electric field at a point given by this dude. And then you sit back and you go, what class does this guy think I'm in? The shit,
Isn't
man.
it like physics or something?
Yeah, totally physics. Lambda is the charge density per unit length on the rod, so we're assuming that the charge density on the rod is uniform, so it doesn't change along the length of the rod. You guys have done shit like you rub a rod against like a animal skin or something, and then it will attract your hair and all that kind of stuff. Have you guys seen that before? Listen, you've taken a balloon, rubbed it on your head, and stuck it to the wall. Have you ever done that before? Have you ever done this? Take a balloon, rub it on your head for a good while, turn the water on the faucet just barely, and then put the balloon next to it, and the water will curve away from it. It is the trippiest thing. It is so cool to see. And it's so stupid simple. Just get a freaking balloon and rub it on your head. If you're bald, find somebody with hair. Yes? You with, or rub it on closing. You with me? All right. You don't have to know a damn bit of physics to do this. Okay? It came from physics, but now it's just math. Look at this. Holy shit. What's the only variable in there, though? Where do you look to see what the variable is? We just did it, guys. What tells me what the variable is in this interval?
Oh,
DX.
Yeah, so the only variable is that, yes? Everything else here is a number.
okay.
Okay. Yeah, this one's really cool, the permittivity. You got the permittivity and the permeability of space. And when you do math to it, the speed of light comes out. It's the trippiest thing. We're not going to do that, sorry. So that's what the little f's not do. He's just a number. Pi, you know, he's our friend. 4, you know, he's even a better friend. This is weird as shit. It's a number. B is a number. Okay. Gets to be in there twice. Thinks he's big shit. Okay. So, ignore all. In fact, do you see how you could take all this shit out if you wanted to? Do you see that? Lambda b over 4 pi epsilon. All that shit can come out, and you have 1 over this. Do you guys see that?
Yeah.
Because they are all constants. How do you know they're constants? Because this tells me what the variable is. And they're not functions of x, so screw them. You can get them out of the way. So I think when students see this, number one, you go, that's physics, what's the shit? And number two, you go, no. This is where this semester I've had a few different classes where somebody go, just put, bruh. So I wrote back, yeah. I love that. But don't immediately give up on a problem. Remind yourself, what's the only part of this that really controls what we got to do? The variable. Where is the variable? What's happening to it? Can I do U sub? Will U sub work? This is just like the problem we did earlier, right? If there was an X up here, U sub would work all day, yeah? Damn! So what do I use instead? Yes, everybody's favorite, trig sub. What trig function am I going to use?
Tangent.
Tangent! And what's the coefficient of tangent going to be?
B.
B. Right? So you know the first step. And like I said, all this shit you can pull out. You can get that, just put it out here. Just put it out here. Yeah? Carry it with you, don't forget it. Is that all right? Is that better? Has anybody tried that problem yet? Okay. Did you write something down for yourself so when you get to it, you'll know what to do? Don't stare at me like that, Sarah. All right, did I help at all? Did I help at all? Did you try something? Did you try something already? Did I tell you something that you hadn't thought of yet?
Yes.
No. Yes, I did. Okay. So get that shit out of the way if you want to. Let x equal b tangent theta, and just go to town. Just go for it. Yeah. Brute force that bad boy. It is a definite integral with some really weird limits. Okay. This is a really good example of, I know the problem is talking about physics and all that stuff. None of that matters. The physics is what set the equation up. So what are they doing this for? They are telling you this is an actual equation you would see in electromagnetic class, electromagnetics class. You would see this equation. You would set it up based on the concepts of physics, and then math would take over. So they're like, oh yeah, you're math people. Here, do this shit. We set it up for you. Well, all right, we can do the integral. Sure. Maybe. No? You all hate me. I suck. That's okay. I'm used to it. Yes?
Plug in the L minus A into the, whatever it is.
After you integrate it. Yeah. You do this the same way as always. Now we're going to do a trig sum.
Yeah.
So you could change the limits. Or you always could leave the limits as long as at the end you bring x back. Don't throw that shit in for theta, because that's what x does, not what theta does. So either change the limits, or at the end you have to bring x back. And both are roughly the same kind of amount of math. Yeah. I do kind of recommend that you change the limits, especially if you're going to do Calc 3. Because a huge part of Calc 3, you got triple integrals. And you have to change the order of integration to change the limits based on what you did. And if you don't get much practice at changing limits, that's even worse. Okay, maybe. I don't mean to scare you, but it's awesome shit. Triple integrals. Anybody ever heard of triple integral before? A little bit? Double integrals, triple integrals, okay. Alright, they're waiting for you. Is that okay for that problem? I mean, I want you guys just to get in there and try it. A lot of stuff is constants you can pull out of the way. Here's a trick. Not a trick, but so help me out, guys. So each one of these things is a number, especially m and especially m, yes? So what is lambda b divided by 4 pi epsilon naught? Don't tell me what the number is because you don't have a clue, but what is it? It's some number, yes? Do you know what that number is? So I'm going to call it w for what the shit. So you can rewrite this whole thing as the integral of w over x squared plus b squared to the 3 halves dx. Does that look better than that? Does that mean the same damn thing as this? Yes. I've just collected all this, whatever this number is, I just put it all together. If that was 7 and that was 8 and that was 4 and that was 2 and that was 7, I could figure out what that number was. So that's a little, not a trick, it's just a truth. As long as at the end, you don't leave w in there. You replace it with this, yes? You just made things look better in the middle of your problem. You're always allowed to do that as long as you bring back what it actually is. Real quick, since I'm on this topic and I can't seem to stop myself. This will come up at some point, so let's just do a nice one. Let me pull back out. Yeah. Can somebody please factor this for me? Huh? Oh, sorry. Thank you. I was freaking out. Too many things I can do. All right. There we go. How do you factor that? Yeah, cool, right? Is that okay? Come on. It's got to be a bread and butter. It's beautiful shit. That's the difference of squares, right? So I got 2x's, so I put 1 there, 1 there. I got 2y, so I put 1 there, 1 there. Different signs, so the middle term cancels. That's the idea of it, right? All right, so how do you guys feel about this? I want you to factor this. How are you feeling so far? Do you see how that's a difference of squares? If I call this business u, and I call this business v, this is just u squared minus v squared, yes? Mm-hmm. All right, so that's something that hopefully you've run into before, where you can replace a disgusting piece because you want to see the form better. Now that I've done that, I see the form better. And this, of course, is u plus vu minus v. And now you just replace u there and there, you replace v there, and then you're done. So you can work with the form and bring the details back in later. That's basically what I just did with that W idea. And again, you don't have to do that. You don't have to do that. It's just a really cool thing you can do. Okay, I'll stop. Anything else from homework stuff? So, let's do this. I've got a handout. I know you don't believe it. But I want to go over, so I want to remind you about the type of integral we talked about last time from 7-8. I want to show you the other main class of integral you're going to see in 7-8, and then we're going to go back and do a little bit of 7-7. And then we can finish that up this Thursday. So here's one integral here. Maybe I can pull the problem out of here. Oh, I haven't done that one yet? No. That would be a good one to do. You actually be able to see it. Yeah! Okay. This is a good little reminder. Look at this bad boy here. So really quick word from people that don't like to write a lot. When you're just doing intervals for yourself, you could skip a lot of steps. That's fantastic. When you're doing intervals for me, for like a paper or journal or whatever, intervals are every damn step. I am not, dear God, I am not allowed to plug infinity in. Yeah? Because if you plug infinity in, that means you found it, and I want you to bring it to me and show it to me. And that's my theory as to what was in the briefcase in Pulp Fiction.
Bring it to
It was infinity. You don't have to watch Pulp Fiction, sorry. So how can I rewrite this based on what we did last time? I can't use infinity, so what do I do instead to give me something I can use as a middle step? T.
Right?
So the limit is?
The limit is t
Yeah.
approaches infinity.
Yeah. Now here's the problem. I've got two separate things going on, right? So before we go there, let me see if you guys remember this. Couldn't I do this?
Oh yes, but
And without getting too in the weeds, I'm not going to say too much about this. There are different types of calculus out there. So the version you learn at this level is a specific type of calculus. It's basically not Cauchy. Cauchy's this guy who did a lot of shit. When I have an interval that's going from negative infinity to infinity, I really can't write it as negative t to t. Because I'm not allowed to let both sides go to infinity like that. I can only do like a ray instead of a line. I don't know if that makes sense. Okay. So you'll see the examples do this for you too. But so how can I rewrite this first guy? In fact, I can be more. So I can say negative infinity here if I want to, right? So then this will be t to 0 plus the other guy's got to go to what?
0 to, oh, to
Infinity for the t, and then 0 to t. I like it. Okay. Now, if you're like young Jeff, I always thought this was extra work, but there's some good concepts behind why you can't do that. Does anyone remember the integral of 1 over 1 plus x squared? It's the one I said.
inverse tangent.
Yeah, inverse tangent. Yes. So this will be limit as t goes infinity, negative infinity, sorry, of the inverse tangent of x from t to 0 plus the limit as t goes to infinity of the inverse tangent from 0 to t. Let me stop for a minute. So most of what we're doing in this section is the same kind of stuff we've already done, just with one extra step. You got to throw the limit in. Because otherwise, I can't. What's the next thing I'm going to do right here? I'm going to plug
You're
a
gonna have to plug
0 in,
the-
I'm going to plug a t in, and of course, if I had left infinity here, I cannot plug infinity into a function. But I can plug t in and then let that go to infinity. That I can do. So what do you get when you plug a 0 in? Here, let's just write it out. Tangent inverse of 0 minus inverse tangent of t. And that's the limit as t goes to negative infinity. Limit as t goes to infinity. Inverse tangent of t minus inverse tangent of 0. Now, what is the inverse tangent of 0? That shows up a couple times. What do you ask yourself when I ask you what's the inverse tangent of 0? Can somebody describe the answer to an inverse trig question geometrically?
It's an angle.
Yes, because what do I take the trig function of? An angle. So what's the inverse trig function's output? An angle. Because what an inverse function does is it takes the domain and range and flips them. Yes? So what angle makes tangent 0?
When sine is 0.
When sine is 0. And what is sine 0?
At 0.
At 0, good. So the inverse tangent is 0. Is 0. Now, does anyone have a clue? Does anyone remember? All right, real quick. Can anybody draw a tangent? Tangent theta. One cycle of tangent theta. Go ahead. Nice, nice, nice. It's basically cubic, but why is it not a cubic? Because what's happening at the ends here? There are asymptotes. Where are those asymptotes at? Let me see from your perspective.
It would be.
Is that right? No, from your perspective, here to there. There it is.
I want to say
Negative pi over 2
pi over 2.
to pi over 2.
Pi over 2.
Let me stop for a minute. You guys with me? How do you remember that? What's on the bottom of tangent?
Cosine.
It's going to be undefined when cosine is 0, and cosine is 0 at odd multiples of pi over 2. Yes? Cosine don't like it on the y-axis. So it's not going to like any odd multiple of pi over 2, yes? So tangent is trapped between negative pi over 2 to pi over 2. So when I invert it, my outputs go from negative pi over 2 to pi over 2. Yes? And you guys have seen the graph of inverse tangent?
Mm-hmm.
Not surprising that it looks like a cubic that fell over because that's what inverse functions are. Yes? They had a good or a rough night. So the inverse tangent, as the input goes to negative infinity, so as I go to negative infinity, what do my outputs go to? Negative pi over 2, good. Plus, as I go to infinity, what do my outputs go to? Pi over 2. And of course, we already did that one. So what's negative pi over 2 plus pi over 2?
Pi over.
What's half a pi plus half a pi? Full pi! Okay. Now, that is trippy. Look at the original integral question. Would you ever expect that pi would be the answer? You might have a little bit because you know this is related to an inverse trig function, so it's not that surprising that pi came out of it, but this by itself seems to have no connection to trig. But we do know it does, so that's why it's not that surprising. Okay, how are we doing out there? So that was an example of one we hadn't looked at yet, when it has a double-sided infinite limit. Yes? I think we did an example last time of just the one side. Okay. I don't think you should see too many of these in the homework. Let me pull one right out of here. Let's see. Here, you guys. Oh. All right, here. Let's do this one together. Where'd he go? Here he is. Ignoring for a minute that there's an infinity, what method is it screaming for?
U sub?
U sub. Why U sub?
Because there's a derivative of.
Yes. There's a function in there whose derivative is also in there. That's U sub. Kick-ass. That is what you always consider first. Because if U sub works, that's like time to have a little party. Because the other methods aren't horrible, but they're definitely worse than U sub. So, first thing I have to do, what's the very first thing I should do? I just want to point that out because I can tell what we're going to have to do, but what's the very first thing I should do?
Turn infinity into
Yes.
t.
Look at the power we have. We can take infinity and turn it into t. And then we can drink that shit. Okay. I don't know what infinity tea would taste like, but maybe that's what goes in the
Probably
drink.
infamous.
Huh?
Nothing. Galactic.
Probably like what? Galactic?
I said infamous.
Yeah. Sounds like something Starbucks is gonna have. Infinity tea now, only $30. Okay. So, how does this work? U is ln x, du is
1 over x.
1 over x dx. Cool. Let's change. Now listen. changing the limits, let me show you this. If I change the limits, I don't want to say this. Nah, things don't get too weird. They get a little weird sometimes. But let's see. If I change the limits, this is describing what x does, yes? So when x is 1, what's u? When x is 1, u is 0. Yes? Natural log of 1 is asking you, what do you raise e to make it 1? And when x is, what's the other limit?
T.
T, what's u? I wrote it. Okay. Yes? Alright, so now I can redo this using my substitution. Take a minute, try to rewrite that using your substitution. If t goes infinity, what does natural log of t do? If t goes to infinity, what does natural log of t do? If I keep, yeah, it goes to infinity. Slower, but it goes to infinity, right? Okay. Get up there. Oh, I'm writing too much. You guys finish up. So what's in this now, if I substitute? U du, yes. U is ln, and du is this. So now this is u du. And what is that integral? 1/2 u squared from 0 to ln of t. So then I get, do you see how the limit's just kind of coming for the ride? So pretty much the first step is write limit as t goes to infinity and replace infinity with t. Then you pretend like it's not there and you just do the integral. And then the last step is let t go to infinity, see what happens. Some of your answers will be infinite. More of them, I believe, should be finite. Let's see, so then I get 1/2 natural log of t squared, and of course when I plug a 0 in, I get 0. So when I let t go to infinity, you guys already told me natural log of t goes to infinity, and of course if I square something going to infinity, the result's still going to
bigger.
infinity. Yeah, good. So this will be infinity. So I don't know if you guys remember last time I talked a little bit about integrals are infinite sums. And if I'm adding up an infinite number of numbers, they have to get small quickly enough so that when I add them, it comes out finite. This function didn't do that. Its outputs didn't get small enough fast enough, so it went to infinity. Here, a related problem that's a little easier. You guys do this one. Can't remember if I did this one last time, but if I did, then do it again.
No, you didn't do this one last time.
All right.
You did one very, very similar.
All right. The first thing I do, replace that infinity with something I can work with. What is the interval of 1 over x? Ln x. I want to go from 1 to t. And what is ln 1?
0. So you get
And
natural
again-
log of infinity,
Well, no,
which
never.
is
Never.
infinity.
Get natural log of t, and when t, as t goes to infinity, this goes to infinity. So we would officially say this integral is, I just put infinity up here, but we would say this integral is divergent. Because this goes to infinity. Okay. So 1 over x is like 1 over x, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Very roughly, right? So that doesn't get small enough fast enough. So, a really good question then. So this is 1 over x to the first power, yes? A really good question then is, did everybody get everything there? I'm sorry. Okay. What about this guy? Ouch. We already know, get out of here. We already know that P cannot be what? What did we just learn that this makes this divergent? What value of P?
1.
So P cannot be 1. Let's throw that out from the beginning. P is not 1. We already saw that that leads to bad things, yes? I want to know, when does this converge? Because everything else is kind of like, doesn't help me do things. Does anyone have a clue how to integrate this thing? How do I rewrite the inside to make it easier to do an integral rule?
X to the negative p?
Yeah. Now just apply the rule. Isn't P a constant? So I'm curious, what numbers could I put there? So P is a constant. Now P represents a lot of constants, but P at any moment is a constant. How do I integrate x squared or x to the negative 7? That's always the same thing. What do we do?
Add 1 and divide by an
Oh
integral.
shit, I forgot one thing. I forgot just the most important thing, John. 1 to
Turn it
infinity.
into t.
So put on that limit 1 to t. Okay, sorry. I got too excited. Just to match up with what we just did. I'm just curious. Is there what powers of P will save? 1 over x wasn't saved. The power of 1 doesn't do it. The power of 1 did not compel it to converge. It diverged. So somebody help me out with the form of the answer to this integration. Don't overthink it. Just what do you do? What do you always do?
X to the negative p plus 1 divided by negative p plus 1.
Yes! Add 1 to the power, divide by the new power. Evaluate from 1, get out of there. 1 to t. So I didn't do anything different right there than if I would have asked you what's the integral of x to the negative 3. You would have done exactly the same thing. Now we have to analyze this thing. Things get a little weird. Things get rather strange. So let me see. I don't want to say this. Yeah, let's do this. Okay. P's not 1, right?
Right.
So what could P be then? It could be bigger than 1 or
Small.
smaller than 1. Okay. So what if P is smaller than 1? You can see another reason why P can't be 1, yes? Okay. If P is smaller than 1, then what's the power on this x?
It's going to be negative.
Yeah, so let's go one more step here. Before I do this.
Actually, technically it would be positive.
Let me do this. This would be x to the negative t plus, get out of there, Jeff. Try it again. This would be t to the negative p plus 1 over negative p plus 1. Right, I'm going to plug a t in. Is that cool? Minus plug a 1 in for x, and I get 1 to any power is 1. So that's just some number, this piece. Do you guys see that? Is that cool? So the question about does this converge or diverge is all about what this piece does. Because this is just some stupid number, yes? I don't care what this number is. If this goes to infinity, this guy can't save it. Let me stop for a minute. So all I did here, I think everybody was with me from here to here, correct? And then I just plugged my limits in. Now, if p is less than 1, what's true about negative p plus 1? P is less than 1, so give me a number less than 1. Yeah, negative 1, right? And what's negative 1 plus 1?
Positive.
It's positive. So if p is less than 1, this power is at least, yeah, so if p equaled 1, this power would be 0 here, right? You guys with me? If p is 0.9, this power would be positive. Yes? Okay, let me stop for a minute. This is trippy. This is trippy. This is what we do together. And this is going to come back in chapter 11, just to let you know. Let me check it again. Somebody cool to this point. Then I just plug the limits in. Now I know p can't be 1. We already proved that case earlier when we did 1 over x. That was p equal 1. Now if p is less than 1, that leads to this having a positive power, and when I let t go to infinity then, what's t to a positive power do? It goes to infinity, yes? So if p is less than 1, this thing is divergent. What if p is greater than 1? Then what kind of power is this?
Negative.
It's negative. So then wouldn't it really look like this? I can flip this down. If p is greater than 1, this is like t squared, t cubed, whatever. What happens here when I let t go to infinity? Goes to 0. So then the answer would be this thing, that would be convergent. All I need. So, real quick. Okay, now let me guess. If p is 1, this interval diverges. It goes to infinity. The instant I make that power anything bigger than, I mean anything. If you make it 1, that new interval will converge. So there's like a knife edge there. It's really trippy, right? It won't converge at 1, but the minute it's just a little over 1, it'll converge. So there's an idea that the function I'm looking at, its outputs have to get small quick enough so then when I add them up, they don't go to infinity. 1 over x doesn't do that. But the minute I make the power on the x more than 1, it does get small enough fast enough. Now, are you going to have to do some of this by yourself? No. That's why we did it together. This was trippy. This is weird as shit. This is stuff you're not used to. But you see some of the logic behind this. I did the 1, and then I said, well, what power could make this converge? So in our future, this is going to be related to something called a p-series, because math people are very creative. It's got a p in it. Okay. Now, here's the other kind of integral you're going to see in 7a. So now we're back to stuff you're going to be doing yourself. And to that end, I'll take one right out of the homework. Look at this problem. Why, at first glance, does this not look like a problem that should be here? Number 36.
Because it
Look at the
doesn't have
limits.
an infinity.
Yeah, it doesn't have an infinite limit, but what does happen At some value, there's some kind of infinity that happens. You see it? Yeah. If x is 5, the function inside,
Asymptote.
there's an asymptote of 5. So the values, if I let x go to 5, this will approach infinity. The outputs will become infinite. We'll get larger and larger of outbound, if you want to be precise. Let me stop for a minute. So we saw one that was really in your face. There's a freaking infinity in the limit. That's obvious that you have to do a limit to go to infinity, blah, blah, blah. This one, am I allowed to plug a 5 in to that function? Am I allowed to plug a 5 in to that function? No. I have to approach it, don't I? So again, this whole idea of limit that you learned in calculus in chapter 2, and then you felt so good when you got out of it, and you learned the shortcuts to the derivatives, remember this?
Mm-hmm.
It's a useful ass tool, dude. It's going to keep coming back. Why did we create it in the first place? Because there are weird things that it didn't want to deal with. And to get really close to it and say, what's happening? But don't touch it. Okay. So, let's do this problem. Where'd it go? 36 was 0 to 5. Now, can somebody tell me how I need to rewrite this? What do you think?
Can you make 5t?
Yeah, the limit as t goes to 5. I love it. You always just make the thing that causes weirdness. Infinity directly causes weirdness. Here, 5 is indirectly causing weirdness, yes? It's not obvious, but when you look at the function, oh shit, 5 is going to freak this out. How can I rewrite this so it's better for calculus?
Negative fractional power.
Yeah. Careful. Yeah. You might have said that, but I might not have heard you. Right, if you guys have had me before, you've heard me go at least on one rant about I wish root notation didn't exist. Okay, I'll stop. No, I won't. I can't. Can you guys please integrate that? Can you guys notice you don't need u sub because the inside's linear? You just got to be careful about a negative. Let's see, can you guys, don't even worry about the limit, just do the integral. Rewrite the limit, just do the integral. So whenever the inside is linear, it's sort of like if you took me for calc and I taught about chain rule, I always said something, this is something to the this power. How do you do something squared? The 2 comes down in front of something times something prime, yes? So this is something to the negative 1/3. How do I integrate something to the negative 1/3? It becomes something to the 2/3, right? Because you add 1.
And then it would be the reciprocal in
It's
front.
reciprocal out front. But what's the one thing I got to be careful about because my poor little something has got something to say? His derivative would have a negative, and since my original function did not have that negative, there must have been a negative on this function to kill the negative that would come out. Now, if you don't like that, you can let u equal 5 minus x, and you'll see the negative come, blah, blah, blah. Just trying to save you some steps. So there's a negative here because of that negative there. If this was minus 2, I would have put a negative 1/2 to kill the negative 2 that would want to come out. And this is, of course, from 0 to t. So this specific function, the original function I'm working with, at 5, there's an asymptote, yes? Let me see if you guys are cool with this. Did we just do, hey, real quick, okay, let me see. Well, let's finish this up and then I'll do what I'm about to do. Computationally, can you just do this? This will be, just throw this stuff in there, yes? And when you plug a 0 in, be very careful, because you do get something, you get whatever the hell that number is, yes? That's trying to be a 3, poor little guy. What happens when you let t go to 5?
You get an asymptote,
No, come on.
or
You get 0 to a positive power, 0, yes?
yes.
So this goes to 0. So my answer is 3/2, 5 to the 2/3, whatever the hell that is. So was the answer infinite?
Yeah. No.
No. So did this diverge? No, this converged. So we would say this is convergent. Like it.
It's 4.39 roughly.
Okay. I wasn't even going to try to do that in my head. Oh, I could have. Oh man, it's okay. Real quick, can you guys tell me, without doing anything, if you've been paying any attention, will this converge or diverge?
Converge.
Why?
Because the power is greater than 1.
Power is bigger than 1. So if I have 1 over x to a power, as long as that power is more than 1, it will converge. Real quick, on the domain 1 to infinity, I think we did this last time. Can you draw a rough sketch of the function 1 over x squared? From 1 to infinity.
Oh.
So don't give me no vertical asymptote shit. So as you start at 1, as you go, wah, yes? Yes?
Yeah.
Okay. So, we talked about this last time. This seems like it's going to be infinite. Because does this ever touch the x-axis?
No.
Isn't it always some area that I'm adding? But it gets smaller fast enough. It's just like the 0.1 plus 0.01 plus 0.001. That's an infinite series of numbers. But it will add up to be 1/9. That's all it is. Nowhere near infinity. Now, the one we just did, where was the asymptote? Up here. This guy. Where was the asymptote? Where was the asymptote? What kind of asymptote is it?
Horizontal.
What is 5? What is 5 is the asymptote? Yes. It's vertical. Yes. So at 5, this thing shoots up. Do you see how? I really want you. Does everybody sort of get this idea? This goes forever, but the area gets so small so quick, it doesn't add to infinity. Just like 0.1 plus 0.01 plus 0.001. This is just the same damn thing turned around, yes? So that's why it immediately makes sense that some of these problems could be convergent as long as this gets small enough the same way this did. Okay, maybe. Screw you, Jeff. Just tell me how to do a problem. Jeff. Sorry. Let's get somebody like, this guy can't just tell me how to do a problem. Alright. Okay. So that's how those work. So get in there and try those out. So the rest of the evening, we're going to go back to one of our favorite things we ever did. In fact, let's do this first. Let's go back in time. I want to approximate the area under f of x. Oh, what do you want, Jeff? Equal. Doesn't matter. No. Just make it 1 over x plus 1 from x equal to 0 to 2 using 4 rectangles. Oh, shit.
7.7?
Does this bring back any, hopefully not too traumatic, huh? Nightmares, maybe?
See, this feels okay, but I know that it's
This
going to turn
is
into
just
trapezoids.
rectangles, yes?
Or not-
So
Yeah,
it's
trapezoid.
really easy to get lost in the weeds, but all the details are just figuring out how tall the rectangles are, how wide they are, and then you multiply that shit. That's the whole idea. And then you add them all up. So, let's do a rough sketch of the area that we're talking about. Let's give ourselves a nice, so 0. I want to use 4 rectangles. Let's do this right now. How do I figure out the width of each rectangle?
It would be
2 minus 0.
Yeah, I want to see how far do I have to go, divided by how many rectangles I want to use. Will tell me how wide each rectangle has to be. That's just physical reality. If I wanted to cover this wall with 10 panels, how wide would I make each panel if I wanted them all to have the same width? Well, I have to know how long is the damn wall divided by 10. That'll tell you how wide each panel is. That's the physical idea that we're using. Okay. So the width is 1/2. Now, get off my head. When I put a 0 in, what do I get out? Holy shit. So I'm going to make my scale nice and generous for myself. When I put a 1 in, what do I get out? 1/2. That's crazy. When I put a 2 in, I get 1/3, which is about 0.33, which is about right there. Okay, how we doing? Now, what other ones do I want to plot? So let me kind of identify for myself what I got here. So it's 0, 1, and then it's 1.5, and then I'm going to put next to this guy 2.3. Let me just put 1/3. I might as well investigate the half points, right? Because my width is 1/2. Yes. So what do I get when I put a 1/2 in? 1/2 plus 1 is, 1/2 plus 1 is 3/2. 1 divided by 3/2 inverts it, so 2/3, which is about 0.6 blah blah blah. So it's about right there. Is that cool? So that's lining up nice. Look at that. So you put next to this guy 0.5. What did we just say? 2/3. And when I put in, let me indicate these things. 1/2. 1. When I put in 3/2, what do I get?
2/5.
Yeah, because 3/2 plus 1 is 5/2. 1 divided by that inverts it, so that's 2/5, which is 0.4, which would be about right there. Look at that. Sorry. That's pretty good. Look at us go. This is 1.5. This is 3/2 0.4. This is trying to be just a 1/3 there. Okay. Now, what have I not told you that you need to know before you can do this approximation?
If it's left side, right side, or middle.
Beautiful. It's the left endpoint, right endpoint, or midpoint. Yes? How do I feel? Let's just do right endpoint. So how tall will the first rectangle be if I use right endpoints? Yeah, because I have to base the height of the rectangle on the right side of the rectangle. So my first rectangle is going to be like that. So eventually, of course, this is going to be over or under. Which one, overestimate or underestimate? Underestimate. I thought you were giving me like a, no, kill him. Send out the lions. So then each one could look like this. Oh shit, I missed. Okay, there we go. Don't look at the projector, Jeff. There you go, buddy. Look at you. And then, of course, finally, I always double check when you do this. I mean, one of the most common mistakes is I get people that do too many rectangles because you kind of get trapped in the pattern. But 1, 2, 3, 4. Is that how many I want? Yes, they go. Thought for a minute, so it says. So now it's just really finding the area of each rectangle. Don't worry, we're not going to go into the detail. I don't know if you guys remember, 5/2 is this, and 5/3 got into the. Do you guys remember sum of I squared, sum of I cubed? You guys remember that at all? Does it bring back any memories? Whoever your teacher was, I'm gonna go snap. All right. Or you could have just
my
forgotten.
teacher is you.
Yeah. Well, do you not remember? Do you not remember?
Do
You remember? Okay, I was gonna stop.
I do remember.
All right. How do I get the area of the first area of the first rectangle? Yeah, the width is 1/2 for each one, right? So in general, it's the width times the height.
Yeah.
Does that look familiar? And then I'm going to add them up, and I've got 4 of them, yes? All right, so that's all that means. The width times the height, add them up, and I got 4. That's all that means. That's it. So the trick was, I'm going to have a 1/2 times every height, so I might as well pull that 1/2 out. What's the height of the first rectangle? 2/3. And then 0.5, and then 0.4, and then 1/3. And that one's nice because 2/3 and 1/3 is 1, so I get 1.9. Cut in half. Is 0.95. And that we said was an underestimate. So I could make you do the whole thing again with left endpoints, and if you did it, remember a lot of the work you need for left endpoints you already did. Yes? Okay, is this coming back? Now, we're not going to do this. I just wanted to do an example of what we've already done. What we're going to do in this class is we're going to add 2 extra possibilities. Why are rectangles nice? Because their freaking areas are easy. And it's very easy to crank up the resolution by just increasing the number of rectangles we use. Okay. The ideas we're about to do then relate to other ways to do this with other shapes, and those relate to other methods you use for other things. So they exist for a purpose. So I think I said last time, do you remember the shapes I said we're going to use last time? Trapezoid. So that's, believe it or not, something we call the trapezoidal rule. And then the other shape is going to be parabolas. But that's not the parabolic rule. We give Simpson credit. We give it, Simpsons did it. So it's Simpson's rule. I forget his first name, so I'm sorry. We'll say it was Simon Simpson. Alright, so, real quick, you guys need to help me out. If I give you some trapezoid, what do I have to tell you so you can tell me the area of it? What do I have to tell you about it? Do you guys remember?
The length.
Gotta know this length. I also have to know
Top one.
this length. And I need to know the height. Now, just because I feel like torturing you more than I normally do, let's prove the freaking formula for trapezoidal area. If I do this, can you guys see the 2 triangles I just created? Did I make 2 triangles? The area of this one, I'll call this one 1, this one 2. The area of the 1 is 1/2 the height times the base, yes? What's the area of this one? How tall is it? H, yes?
H, yeah.
So it's 1/2 the height times the base, yes? So what's the area of the trapezoid? Add those dumb things together, yes? And then can factor out that, there. So a triangle is 1/2 height times base. 1/2 height base, no trouble. And a trapezoid has 2 bases. So it's the same formula, 1/2 height times, oh, I better use both bases. B1 plus B2. How we doing? So rectangle, the height was the function value, yes? And all I needed was a width. This one, I'm gonna need a little bit more. So you're all very excited, okay. So let's look at the general idea that we're going to use now. Okay, here we go. Already did a lot of this. Oh, cool. You gotta not forget that. Oh. So let's kind of develop this with like a generic function. Let's just bring you back to your Math 180 days. How many times did your teacher draw this picture? Yeah.
Can you zoom out?
Sure. Oh, you need something from up above?
Yeah, I need the formula.
All right, so I'm going to, so we want to find the area under this curve from A to B. So I'm going to call this f of x. I'm going to call AX0 our delta x. I don't have to get all this detail-y, but remember that's the formula for it, but I just need to know delta x right now. Yes? So I'm going to draw kind of like an imaginary where the x1 would be. Put little dots saying I would continue to break it up, yes? So I want to focus on that first section, because then whatever I do for it, I'm just going to repeat that. That same idea. Yeah, same way we did with rectangles. Now, do you see how this curve is not very extreme? So do you see how the trapezoid actually fits it better? Okay. Now, if, real quick, don't draw this, but if I had a curve that was more extreme, and I break this up, then a trapezoid actually leaves a decent little chunk on that. So it all depends on, how extreme the curve is, but we're going to analyze the amount of error I can expect for each method and which one seems to be the best. So how do I figure out this guy's area? Can somebody identify, now this is where the first thing we notice is different. What is the height of that trapezoid? You guys see the trapezoid? You guys see the parallel sides?
Yeah.
Where are your bases then? Your base are belong to me. Huh?
The sides.
Yes, exactly. These are the bases. So where's the height?
Delta x.
Yes, delta x is the height. Kick ass. So, delta x is the height. You guys see that? So it's just a trapezoid somebody put on its side, yes? The height is delta x. For every trapezoid I'm going to draw, or that I could draw, the height will be delta x. It's just a poor little trapezoid somebody put on its side. It's all like, eh. What is the length of the first base here? You can do it. You can do it. Come on. What's this length?
F of A.
Yes, f of a, f of x not. This length here, just like with Riemann sums with rectangles, I swear to God, just like with Riemann sums, this was the height of the rectangle. Now our trapezoid, this is the height of the trapezoid, because the poor little dude's on his side. These are related to the base, but the way that we found the height was the function value, correct?
Yeah.
So the way that we find B1, since that's where that is the function value again. So what's B2?
X. 1.
No, I need you. Come here. Okay, how we doing? Now we're going to end up with we're going to go through the derivation and we're going to get a little formula that you can use forever. Right, we're going to develop the formula. I'm probably going to give it to you because I'm not, I always hesitate to say this, I'm not overly concerned about this section, but you need to know it exists because the methods we use in this section we use for other ideas in mathematics, depending on how far you go in math. So this is an important section, but for us immediately, it's kind of like an interesting little side note. So what is the area of this first trapezoid?
1/2 delta x.
Let me do it the same way I did earlier. 1/2 h. I'm sorry. You're doing it better than me. 1/2 delta x, because that's h.
Times
B1.
Which is f of x 1 plus f of x.
I like it. Let me stop for a minute. Is that cool? Can you write right underneath that what A2 would be? Don't say it out loud. Just take a moment. What do you think A2 would be? If I go forward and I do the next thing, don't do all the work. You should be able to just see the form of it. What inputs will my next trapezoid be using? X1 and X2. So what will it look like?
1/2 change of x times f of x of 1 plus f of x.
Yes. So, if I keep going and I have, I don't know, 87 rectangles or whatever, they're all going to look the same. But do you notice how each rectangle, each trapezoid kind of overlaps? Do you guys see what I mean? Do you see how I have two? If I add A1 to A2, won't I have two f of x1s? Do you guys see that? If I add A1 to A2, I know I got a half, but I'm going to factor that out. Won't I have two of these? Yes? But only one of those. Yes? And if I go all the way through, what else is going to be one of? The last one. And if we call that xn, there'll just be one of him. What do we got? So, what does this end up looking like? I'm going to have, I'm going to factor out a 1/2 and a delta x. So then I'll have f of x naught plus f of x1 plus f of x1 plus f of x2 plus f of x2 plus ... up to xn. Yes? So eventually it's going to become 1/2 delta x f of x0 plus 2 f of x1 plus, not 3, Jeff, 2 f of x2 plus 2 f of x3. You could do it, Jeff. ... plus 1 poor little f of xn. That's the formula for a trapezoidal rule.
Isn't it like the triangle of 1 and bases? Does that,
Oh. Wait, do it again, sorry.
like, no, I think I'm confusing something.
Maybe. Oh,
I just know there's a
oh,
pattern.
by the way, well, I think you guys are cool. The 1/2 delta x was factored out. I think you guys are cool with what's happening here. It's the same kind of thing we did with, we factor that delta x out when you did the rectangles. Yeah. How do you guys feel about that? Okay. Okay. What time is it? Okay. So let me do this. I'm going to do the derivation of Simpson's rule, which we're using parabolas. So that one's going to take a little bit longer, and then we're going to leave. And then when we come back on Thursday, I'll have a practice test for you. We'll do some examples and such of this kind of stuff. Maybe more of you will have questions. We'll find out. Okay. So, Simpson's rule. All right, this one gets a little tricky. So I got my same poor little dude. Just sitting there minding his own business. And we're just going to identify delta x the same way as before. Did I? Yeah. Okay, good. But now, let me see if you guys, how many points do I need for the equation of a line? 2. How many points do I need for the equation of a parabola? If 2 points make a line, I need 3 points for the parabola, yes? None of them have to be the vertex, I just need 3 points. Stop for a minute. Kind of makes sense, because what's the general form for a quadratic equation? ax squared plus bx plus c. How many parameters are there? 3. So how many pieces of information do I need? 3. I like it. Line, mx plus b. Y equals mx. How many parameters are there? M and b. So that's why I only need 2 pieces of information for a line. Okay, how we all do? So the last one we did, and the rectangles, I just needed kind of 2 inputs, the beginning and end of that shape. Yes? X9, X1. Parabola, for every parabolic piece, I need 3 inputs. X0, X1, X2, for example, for like the first one. You guys, I love you guys. Okay. Does that make sense? A little bit, okay. Also, to make the derivation easier, if, do you all agree that this shape here has an area? Is that somebody's, oops, this shape here has an area? Y'all agree with me? Y'all agree with me? Is it different now? No, okay. So I could move that whole thing to wherever I want to on the x-axis, and the area is the same, correct? All right. So we're going to do something that will make the derivation of this rule so much easier. I'm going to move that back a bit. Okay, so first off, I'm going to show you, here's the idea of Simpson's rule. So I have x1, x2. And then I fit a parabola through those. Oh boy, that's terrible, but you get the idea. Do you see how automatically Simpson's rule is going to be better than all the other rules? Because it's going to follow the curve more effectively. I'm going to need less iterations of the rule to get a good approximation. So a lot of what we're doing in calc, the further you go up in mathematics, the more it starts to overlap with computer programming. So a lot of what we do kind of relates to making a more efficient computer program. Yeah. Okay. Do you have to know computer programming to do this? No. I'm just saying. It's related to it. Okay. Now, I'm going to move this back, and I'm going to work with this. Let me put it on the next page. I'm just going to move this. In fact, let me see, this first chunk. I'm just going to focus on this first chunk. Yes? I'm going to move it back so it looks like, oh, Jesus. Okay, all right? I'm going to move it back so it looks like what, Jeff? And you are all over the place. Oh, did I pick up that paper? It doesn't matter. Oh, there it is. I'm going to move it so it looks like this. Let's see if I can make it look sort of the same. Where'd it go? Doesn't matter, Jeff. Yeah? Okay. So everybody, so I just took, oh boy, give me a little creative license. This, and I moved it back. Just moved it, so now it's kind of centered around the y-axis. Yes, you guys with me? Now, I'm going to do even more. I'm gonna, what is x1? The way I move this? 0. So whatever x0 and x2, do you both, both of you. Sorry. It's the opposite of being drunk. I'm so sober that you all are becoming less people. Whatever x0 and x2 are, they're equidistant from both. In fact, they're like delta x. But I don't want to have to keep writing delta x. I'm going to call it one of our favorite little dudes. I'm going to call it h. So this is h up. Is this cool? And this is negative h. This is h down. However far they are, they're the same distance. And I'm going to call it distance h, just to make things easier to look at as we go through this derivation. Okay. I love you guys. Now, remind me again, what's the general form of a quadratic?
ax squared plus bx plus c.
Okay, I like it. I'll make it all capital, be all nifty. And what points are we using for our parabola to go through? You can do it. Negative h. This would be f of x naught. Jeff, you already have a comma. 0, f of x1, and h f of x2. Is that cool? I know I'm mixing some stuff, but we'll get there. Actually, let me be even better. Let me just call it y0, y1, no Jeff, y2. Is that cool? Whatever the output is for x0, I'm going to call it y0 because that kind of makes sense. And again, it's just so we can see things better in our derivation. How we doing? Okay. Now, real quick, do y'all agree that whatever this parabola is that fits through these points, it has this form? It has to. That's the form of every parabola in existence. So how would I find the area in this region? What would I do? I'm going to assume that's the answer, yes? That is what a parabola is. How would I find the area then, underneath it, between this and this? Integral from what to what?
From negative h to h.
Negative h to h of this thing, yes? Now again, we're doing a derivation. I'm doing something weird. I'm going to do two different things, and I'm going to show you how they relate to each other, and we're going to develop a process out of that. Again, this is nothing I would expect you to be able to do by yourself. This was, decades of work by people, and we're just going to do it in a night, because we don't have to go through all the weird shit they had to go through, yes? Maybe not decades, but quite a bit. Okay. Can you guys do this? I mean, it's just a polynomial. Gotta love that shit. So what do you get? What do you get when you integrate this? You can do it. You can do it. 1/3 ax cubed plus 1/2 bx squared plus cx from negative h to h. Let me see if I can. Well, let's see. Okay. I'm just gonna. All right. So you would plug in h, and you would plug in negative h. Yes. Oops. Try to do this correctly. Okay. So everybody with me on that? Plug in h minus plug in negative h. This is 1/3 h cubed minus negative 1/3 h. Yes, the cube makes it negative still. So this is 2/3 ah cubed. Is that cool? This is 1/2 bh squared minus 1/2 bh squared. Yes, the square kills the negative. Yes?
Yeah.
Screw you, Jeff? Okay. So these go away. And this will be ch minus negative ch, which is plus 2ch. Okay. And then whatever a and c are, that's actually the answer for the area of that first chunk. Yes? We still don't know what the hell a and c are doing. We're crazy. So we got the answer, the form of the answer. But we still don't know what a and c are. Okay. So we're sort of like, yeah. Let me do one thing to this. Help me out, guys. Do you see how they both have an h in them? So I'm going to factor out an h. And I'm going to factor out a 3. See if you guys are cool with this. An over 3, I mean. Do you guys see that? When I take out an over 3, I actually do what to the things on the inside? Multiplied by 3, yes. So this would become 2ah squared, because it took one of the h's, plus 6c, because I took its h. Okay. Stay with me now. Now, again, if any of you would have thought to do this, whoa, this is weird shit. There's no reason you would ever think to do this. Do you guys kind of get the idea that whatever the answer we get, this is what we would do to it to get the area of the first chunk? So in some sense, that's the answer. That's the area to that first chunk. It's very unsatisfying, because I don't know what A and C are. So good job, Jeff. Okay, so now let's focus on looking at this situation in a different way. So hold on to this. I'm gonna come back to it.
Wait.
I'm sorry. Sorry. Let me do this here.
Okay.
Okay. Going back to this. What were the points that they're supposed to work in? Do you get somebody on that list? What were the points that were supposed to go work in this?
Negative H and Y naught, and then 0, Y1, and H, Y2.
So, I'm sure you guys have done problems like this, where if I gave you 3 points and you plug them in, you can figure out what A, B, and C are, it would make a system of equations, blah, 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 blah. So this is so cool. I really want you guys to be with me on this. Something really cool is about to happen. And you're all like, I don't know what your definition of cool is, man. I don't think it matches up. Okay. So I'm going to plug this information in. Don't I get y naught equals a h squared plus b h plus c? Yes? That's fascinating. Plug a h in for x, I should get a y naught out for y. That's what that says. That has to be true. If I plug a 0 in for x, I should get a y1 out for, look at that, sweet. Yes? Plug a 0 in for x, I should get a y1 out for y, so y1 is c. And y2, plug a, negative h. Let me come back for a second. I'm getting too excited. Negative h, yes? Is that cool? So this would actually be ah squared, h, sure, Jeff, minus bh plus c. bh? Sorry, I'm getting loopy. Y1 is C, because when you plug a 0 in, that's what happens. Now I'm going to plug an H in, and I get AH squared plus BH plus C. And that's where I get Y2 from. Okay, now, do you guys see how I could cancel some shit out if I add stuff together? Do you guys see that? I could start doing system of equation kind of stuff to cancel some shit out. Do you guys see that? But there's a very specific thing I want to do. And again, it's not something you might immediately see. But can you guys take a second and figure out what this would be? What's y naught plus 4y1 plus y2? If you take y naught plus 4y1 plus y2, yes? So you really just add y naught and y2, and then add 4c to that. Do you guys see that? That's all that says is do it. Let's see what you get. Don't say it. Just do it. Or stare at it, I guess. So you guys see how I'm just adding y0 and y2. What do you get when you add y0 and y2?
AH squared plus 2c.
What do you get?
2AH
2ah squared
plus 2c.
plus 2c. And now I'm going to add 4y1. Yes? So y0 plus 4y1 plus y2 equals 2ah squared plus 6c. Does that look familiar at all? This was the area of region 1 of that first parabolic piece, yes? So then every chunk, the first parabolic piece, the second parabolic piece, would follow what we're doing right now. So if I just do this, what's missing? This is almost the same. What's missing? H over 3. So if I multiply this by h over 3, that will be the area of the region 1, I guess you can call it, right? That first parabolic piece. And then I could do, now, so what would the second parabolic piece look like? Well, it would start at y2, and I would add 4y3, and then I would add y4. Yeah, so the first parabolic piece, let me go back to this. Where'd it go? Where'd you go? Dadgummit. Who knows? I forget. It's gone. Oh, here it is, right here, Jeff. No, not really. But if I kept going for the rest of the shape, I would just go to the next piece, and it would start at x2. Do you guys see that? And then I would do a parabola through whatever its points are. So if I add the next piece, it would, you can start to see the pattern here. Start at y4 plus 4y5 plus y6. So you're going to get 4y, and then you get 2y2s and 4y3s and 2y4s and 4y5s and 2y6s, yes? So, let me give you this. Let me show you the final form of this monster. This is back. Where we have internet, so they didn't have a PlayStation back. When they only had games, they just sat around and did this. Play this stuff.
If you have all the information to do that, you already have all the information to do it. So how do you not just do it?
So. Oh yeah, yeah. We'll do the details next time. So you see how this is what it ends up looking like. Notice it have to have an even number of subintervals. I can only break it up in 2, 4, 6, 8, or else I can't divvy them up correctly for every parabola. In fact, I need 3 points, and it overlaps with the next one. I need an even number of divisions. Now, I'm not going to do Simpson's rule. I'm sorry. The error, we'll talk about that next time. We'll do the example next time. I think we've done enough today. This is plenty. You guys think so? You guys okay with that? Is that bad? You okay? You feel like you're getting gypped out of, or you're not getting your full worth? I actually had somebody complain about that one time. Okay.
Really?
Huh? Somebody said,